I will talk about Bayesian models, specifically in reconstructing and analysis of medical images, in particular MRI. So it will be, machine learning plus the application side of it. I'm going to talk about two problems that are actually at the very center of using MRI in the clinics and using MRI in research as well, which is one of them is reconstructing the image from its measurements. And the other one is given something that shouldn't be there in the image, being able to detect it. So what the radiologist or the clinical expert would do naturally. Before talking about all this, I want to acknowledge the people who actually made this possible, my collaborators, and the students, Karen, Shoran, and Jaden, and the funding agencies. So before going into that, let me just give a very brief recap about generative modeling. How many of you are familiar with Bayesian models or generative models? Okay, so I think this might be useful for the others. The main idea in probabilistic modeling is to be able to model the joint distribution of observations and the identity of interest that we're after. What does that mean? The observations can be the image itself, in which case the identity that I would be after would be, for example, the semantic parcellation or the segmentation of the image, or a class assignment, or maybe the phenotypic information. It can be measurements, for example, in MRI, it can be the case-based measurements, and then the identity of interest that I would be after is the image itself. It can be segmentations, then I might be after something else, and so on. So it's really the relationship or joint distribution between these two entities. And there are really two different models that the factorization is quite important. First one is the observation model. So given the identity of interest, how did I generate the observations, which encodes the physical model? And the other one is our prior. So what should this identity of interest be in real life? What are plausible answers? To give a very simple example, let's talk about a case where we have very high resolution, high SNR MRI images of the brain that we see on the left-hand side, which are the identity of interest that I'm really after. So that's, in this notation, is the M. In that case, the prior, P of M, would be the distribution of what are the plausible MR images, what are the plausible anatomies. On the right-hand side, we have the observation, so the noisy version of it. So the probability of Py given M, the likelihood model, is how do I generate the observations from the identity of interest. Quite simple. So the generation of physical model. The usual thing to look at in these cases is the posterior distribution. So I usually have the observation. I want to get an idea of what the identity of interest was. So there's a process of updating my belief. I start with my prior belief, I have an idea of what plausible anatomies and MR images should look like. And then I update this idea with my observation through the Bayes theorem. So there's a group of people in optimization they're mostly familiar with, which is the data regularized optimization ideas. And then actually it nicely fits into this entire probabilistic framework because a basic optimization problem can be defined as finding the maximum or the map estimate, maximum posterior estimate in a probabilistic model where I would have, for example, the data term that links identity of interest to the observations or the physical model, and my regularization or my ideas about what life should be and how the identity should form. Just a small parenthesis here, feed-forward applications of the neural networks, for instance, would fall into another category, which is directly going from the observations to the identity of interest in one mapping. So we're doing something slightly different. So besides this notation, graphically what we're doing is actually quite simple. So I have a space of plausible images, P of M. Let's assume that kind of gives this very nice curved structure. And this is a completely artistic illustration, so it's extremely inaccurate. But for the sake of illustration, it's helpful. And then I have this small gray ball here, which is formed by the observations that I see. So this is the ball where each image in this ball actually satisfies the observations perfectly well. As I go away, the constraint, or they satisfy less and less better. Now, this ball is formed by the likelihood model, and this guy here, the curved thing, is formed by my prior understanding of the real world. What I'm after is actually that red area here. I want to characterize that area. Specifically, for instance, I want to find the point on that area that achieves the maximum probability satisfying both my initial belief and the observations. Very simple ideas. Okay. What we're going to discuss mostly is actually this guy here, how to form the priors. So these theories, or how to actually create these probabilistic models, is very well understood. It's been studied in the machine learning and statistics community before that for a very long time. What is new now is we have much more powerful tools to build these curved structure. Okay? So specifically, I'm going to talk about how to construct that, and how can we find the area here or the maximum point in there. Okay. So in this entire thing, what can the networks offer? Now, the big problem with actually creating a distribution over real life, over all possible images, is obviously the dimensionality. M is of image size. If I'm talking about 200 by 200 images, that's nicely 40,000 variables for you. Being able to define probable distributions or estimate distributions in 40,000 dimensions is a difficult task, and we don't really have any tools for doing it properly. So one way that people have been using quite a bit in the past is the latent variable models. Idea is quite simple. Instead of saying that I want to directly estimate distribution of this 40,000 space, I'm going to say that, you know what, actually the real dimensionality of the space is much, much lower. Okay, and I'm going to say, and that I can actually define as a latent space, and that will act like a Euclidean space. So the main idea about the latent variable model is to say, why don't I then just say that I define a probable distribution here, P of Z, in a much, much lower dimensional space, and then I formulate how to transform the Euclidean space into the space of images or the subspace that I'm after. Now, one model that most people are very familiar with is the principal component analysis, which is a direct application of this. In principal component analysis, well, most people know it from statistics, but actually it's also a probabilistic model. The idea is, it's exactly this. Now I have my latent space, Euclidean space. I define the transformation as simple linear mapping. In this case, that basically means that I take the Euclidean space, Z, and just rotate it into the higher dimensional space. Okay. So the space of the things that I'm interested in becomes a hyperplane in that 40,000 dimensional space. Now this is nice, but obviously there is a very straightforward extension of this, which is to say, instead of having hyperplane, we can maybe allow for generic manifolds or generic surfaces to be formed using these ideas. This idea has been proposed back in 1995. There was a paper which somehow has minimal number of citations, probably because it was published in non-machine learning community. But David McKay actually had this idea, said that, you know what, we can just take PCA and instead of having a linear map here, put a neural network. And say that if I have a neural network, and if the neural networks, and at that time it was known that, well, you know what, they can actually approximate very complicated functions, then I should be able to allow these very awkward surfaces. So he said, why don't we just do this? Well, optimization was kind of not very well understood back then, so he was saying that I'm going to have a number of samples, so I want to optimize really the likelihood of this model. So optimize for the parameters of the network, and the thing that I know, being a physicist, I will just do Monte Carlo integration. So sample and integrate and try to optimize the sum of the integral, the result of the integral. Now, this is computationally infeasible, especially if the latent dimension even has 10 dimensions, it becomes a difficult problem to sample from a 10-dimensional space. At the very end of the article, at some point, he says that, well, you know what, the obvious extension of this would be importance sampling. So instead of sampling the Z space blindly, you can use importance sampling to do it. Roughly about 20 years later, variation autoencoders actually did this. So they use importance sampling to solve this problem. And the main idea is, as a posterior distribution, they don't use anything, but they use yet another neural network to estimate the posterior distribution for the importance sampling. Okay, a lot of notation, a lot of math. What ends up being useful is actually these models with the nonlinear maps, so putting a neural network in that mapping from the Euclidean space to the curved space gives us a huge advantage. On the left-hand side, I actually take an MR image from the brain and cut patches of 28 by 28. And there are real patches on the left-hand side. In the center, I actually show randomly generated patches from a model, a latent variable model, that uses a neural network for the transition from the Euclidean space to the image space. Now, comparing with the PCA, so what actually makes a difference? instead of using, the hyperplane, if we use a curved model, is instead of getting these ugly random samples, we can get really samples that actually resemble MR image patches. You can say that, well, you're using the PCA with 60 components and the super nonlinear model with 60 components, which has a lot more power, a lot more parameters. Why don't you use PCA with more parameters? But obviously, if you know this, it actually makes things worse because now the PCA starts learning, or linear model starts even learning noise. Okay, so at this point, I hope I convinced you that actually just putting a network instead of that linear map actually gives you a huge advantage in terms of what you can generate, or how you model the prior belief over what is possible, what is plausible in real images. So what can we do with it? I want to talk about the two avenues that we explored actually leveraging these advantages. One of them is the MRI acquisition. So the MRI acquisition actually is a very long path. Okay, so from the patient to the MRI, there's a very long path. There's a lot of physics and a lot of established physical models there. I'm not going to talk about any of these things, put a nice carpet over it, and I'm just going to talk about this very, very last part. Okay? I'm just going to talk about how do we actually, what we measure is this guy here, and how do we convert this guy into a beautiful looking image. In the very simple view, what MRI measures is actually the Fourier transform of an image. Okay? So we measure the Fourier transform, where I'm showing the magnitude. Obviously, it has the magnitude and the phase. And then if you apply simple inverse Fourier transform instead of the Fourier transform, you get the beautiful image. Now, each line in this two-dimensional Fourier transform costs time. So if I can actually cut down some of them, I can use that time to do other things. To maybe, acquire another contrast image, to have the patient in there for less, to gain money because I can actually now image more patients, so the hospital gains, so everyone is happy. What happens is if I start cutting down measurements, until some point everything is nice, I can still construct the image, but after some point, I actually get huge artifacts in the image. So I don't want that artifacts because actually the entire point of the image is to be able to see the anatomy. If I cannot see the anatomy, that's bad. So then the idea is, let's still try to reduce this as much as possible, because if I have an idea of what plausible brain images should look like, I can simply reconstruct this image based on these few measurements. I can simply get rid of the artifacts very fast. Now, I need two different models. One of them actually is going from the identity of interest, which will be the image itself, that goes to the observations. And in MRI, this is actually quite well understood. I have an encoding matrix, in a simple term, that actually takes the image, applies, Fourier transform, applies the encoding operation, takes into account the different coils that you're using, the sensitivities for the coils and all these physical things, and simply adds a little bit of noise there and spits out the measurements that we see. Okay? So actually, the model, the likelihood model that goes from the identity of interest to the observation is very well understood, and there's no really, you can do improvements there, but to the first order approximation is quite good. What is more difficult is this guy here. Okay? How do we actually create this curved space? So the prior model. And obviously, there has been a huge amount of work on this. I mean, here, especially EPFL is one of the strongholds of compressed sensing. And the entire compressed sensing ideas can be actually seen from completely the Bayesian perspective, right? For example, I can say that, I want to minimize L1 norm or the TV norm of the image, which basically means that I have an exponential distribution with the TV norm on top. I can say, well, maybe I can do kernel density estimation, which people have tried. They can say I can use principal component analysis. For example, people do the KT science and so on, who said that let's learn a principal component from the image and use that as my prior information. You can even go fancy and really start using sparse dictionary learning to really have some kind of atomic elements and sparse distribution, decomposition of the images, and so on. Essentially, with all these things, you solve exactly the same problem. The only thing that you really change is this prior guy right here, basically adding more and more capabilities into the prior guy. So if we apply these images, for example, to a specific case, here I have the original image that's really high resolution, fully sampled, fully measured. And this is basically same image, but instead of using all the measurements, I use 1/3 of them. And then the rest, I simply put 0, so I see these artifacts. Now, if I apply these really fancy methodologies, what I can get is I can actually reconstruct this quite well. For example, here I have the total variation, very simplest compressed sensing framework. And here I have a dictionary learning framework and using the compressed sensing ideas. Now, it all looks nice. The total variation is a bit cartoonish, and the DLMRI looks nice, and so on. What is quite interesting is actually, although it looks nice for the human being, it can actually miss really crucial details. For example, the little triangle here, it's like doesn't really appear in most of them. That's because they don't really have an understanding of the underlying anatomy. So what do? We say, why don't we actually now use the machinery that we've just discussed instead of using ad hoc prior terms or using dictionary learning? We simply feed a latent variable model that's powered by the neural network in the mapping from the latent space to the image space. So this looks a bit awkward, but actually it's very nice because for the computer, there is absolutely no difference between a mathematical formulation and a neural network like this. They're both differentiable, so the computer doesn't really care. But the problem is the prior is actually approximate. So we're not really looking at this picture, but we're looking at a picture like this. So really, we don't really get the intersection very, very well. That's fine. Again, it's differentiable. So what I can do is I can actually do basic gradient descent, or I can actually use all the optimization theory that I've developed over the years for other priors and fit it here. So again, in the graphics, what we do is we'd start from a simple estimate, for example, the zero-field image right here that satisfied the measurements. And then we basically take a few steps towards the prior, and then we go back and say, you need to satisfy the observations. So, map it back to the observation space and do this a few times. So try to find the area that's closest to the prior that I see, yet satisfying the observations perfectly. All this process actually gives you this weird image that looks like heart is beating, but actually the heart is not beating. Every time it looks like there is a beating coming up in the image, in the video, it basically means that you're going back to the observation space. So from that image, you can go down to here. The nice thing is if we compare what happens here is now because we know how the anatomy should look like, we don't really blur it out or put a patch there. Instead, we really put the triangle back there. Because that's the type of anatomy, that's the type of gray matter, white matter structure that we've seen in many of the brain images. So it's easy to reconstruct that. Okay. Comparatively, if you think about, for example, well, you know what, you can also use a neural network, simply just feed the image or the undersampled image and get rid of the artifacts with a filter. You can actually get images really nice as well, that look nice. But again, because they don't have the understanding of the anatomy, they don't really put the structures in there. Okay, so that was actually generating the images. More close to the actual clinical practice, how radiologists deal with things, is the outlier detection part. So lesion detection is an important problem. Given an image like this, the first task a radiologist does is, does this look normal? If it doesn't look normal, which area does not look normal? And what is that area? Then what do I write in my report? And the doctor that's looking at it, what should I do to go on for the patient? And there has been quite a number of work actually to go from images and detecting them automatically, especially in the unsupervised area. So you know what, the supervised learning, what it does is it says, you know what, here are the observations that I have. The identity of interest now is basically the segmentations, which actually parcellates the entire image into areas that do not look healthy and the areas that look healthy. So I know how to use it supervised learning-wise. I basically feed in the observations, have a network with some parameters, tune the parameters with lots of data, and I can get really good accuracies. It's very nice, but I suspect this is not how actually humans do this. So let's do a test here. How many of you are familiar with brain MRI? Fantastic. Okay, so for those who are familiar, it will be easy. For those, it will be a nice test. So this is a brain MRI. Okay, this is a brain. I can say that this is a healthy person because I think this is me. Well, as healthy as it can get. And there's no lesions or there's no abnormal parts. So for most of you who are not familiar with brain MRI, this is the first brain MRI you've seen. Now I show you two brain MRI with something is wrong. Can you identify the areas that shouldn't be there? Okay. You can probably, I hope, some of you actually guessed that, well, this doesn't look really normal, that doesn't look very healthy, and this, well, I haven't seen this in the previous one, so this probably shouldn't be there. And this is fantastic because most of you seen brain MRI just once, a second ago, and now you become a medical expert. You can actually see what shouldn't be there. So humans are fantastically good in this, and computers are fantastically bad in this. So we're trying to figure out how to make computers do it, because actually if we can automate this, then we take the boring or kind of the routine job out of the radiologist's hand to really automate this fast. What we do we again talked about the Bayesian model so much, so we're going to do the same thing. We're going to say that instead of having what real images should look like, we're going to have a manifold or a probable distribution of normative image. Normative distribution basically means what healthy images should look like. What I'm going to do now is, if I have actually an image that has some abnormality, it will obviously not lie on that space. So I can actually use this structure to really identify how do I make this guy into a healthy image. And the difference should actually highlight the abnormal part that shouldn't be there in the image in the first place. So what we do now is we try to model the normative distribution. And this is, again, not a new problem. It's actually an old problem that, once in a while, someone in the literature is crazy enough to take a stab at it, and they get, beaten back because the accuracies are so much lower than the supervised learning, and they step back. But, like most of these labs, they have one of article every 2 years or something taking a stab at it. And the main idea is you take a healthy anatomy and you try to morph the anatomy, deform it into the patient image, and then look at the difference. What we're going to do is something else. We're going to say that, no, we will have this, we have this prior model that actually was able to reconstruct images. So why don't we just train it with healthy images and use that? And the nice thing with this is then I don't really have to deal with the registration. It will be a global model. I can take very large image patches. I can even take the entire image and just model the normative distribution of what brain MRI should look like. Now, again, the application of the same idea. I need basically a model that takes the identity of interest. In this case, the identity of interest will be the healthy version of the image that I see, and the observation will be the image bearing the pathology or the lesion. So I see, let me create a very simple observation model. I have my observation here, my identity of interest, and let me say that there's an additive lesion. Why not? So then I solve basically a maximum posterior problem again, basically kind of a trade-off play between the prior and the observation model. I have my network that I'm going to use from before that I've discussed. And now I'm going to do one assumption and say that lesions are kind of contiguous areas. It's very rare to have a lesion that actually completely spreads across the anatomy. So I'm going to say, get me a lesion that somehow is contained in one piece. So I kind of have an idea of how to encode this from other works, which is kind of the TV norm. What I'm going to do is I'm going to run an optimization again and really do a gradient descent. So I will start from one part and I will simply, optimize TV norm, optimize the prior together, try to move from this initial point to a part where actually I start lying on the image manifold. Now, we did some tests with this as well. So we took, a bunch of images that do not show any lesions. We trained our model with that. And then we used exactly the same trained model on various different lesion data sets. I'm going to show results for two. One of them is on brain tumors and the other one is in stroke lesions. So note that the training itself is actually done on healthy individuals. So the algorithm has never seen a single example of an image with lesions. So exactly the same test that I've just applied to you. I'm going to apply the same test to the algorithm here instead of you. So what we do, when we do this, actually we see some interesting things. If we actually do these Bayesian models and really try to optimize or the trade-off between a prior and observation model, we see a huge jump in the AUC in the detections. What these graphs shows are the AUC in detection in terms of the pixels. So how many of the pixels that have lesions can you identify? The curves that you see here are all variations of the Bayesian framework that I've shown you. The curves that you see here are the non-Bayesian versions. So it's clear that actually there's something interesting going on, that you really can actually, by integrating prior knowledge, normative distributions, and really use old ideas like Bayesian modeling and Bayesian inference or map inference, then you can really get a big boost in the outlier detection. Now, visually, what it looks like is, given an image like this, the algorithm tries to convert it into something normal. And what is the difference here is a part that shouldn't be there. So what I show here is the restored image, the identity of interest, the difference between the restored and the actual lesion image, and the detections at different thresholds, because doctors like thresholded binary images, so different thresholds. And for comparisons, what I show here is a ground truth to compare. So in cases where the lesions are obvious, where the human beings are really good in identifying them, the algorithm is actually doing quite a good job in, identifying the area that shouldn't be there. In lesions where actually even humans have difficulties, believe it or not, but there are actually lesions in these images, then the algorithm is having difficulties. But I think that's normal. With that, I'm going to end, and if you have any questions, I'd be more than happy to answer.